All right, hello statistics. This is for those of you who missed class today. Parameter, a number that describes the population. A parameter is a fixed number, but in practice we don't know what this is. We're going to call this P, all right? That P is for parameter. Parameter is to population, as statistic is to sample. A statistic is a number that describes a sample. We're going to call this P hat because this is a predicted, this is a proportion that describes a sample, okay? The value of a statistic is known when we have taken a sample, okay, just like you did the other day, but it can change from sample to sample. We often use a statistic to estimate an unknown parameter. All right, the proportion of a sample is called a statistic. We will call it p hat. All right, you need to look over questions 5.27 to 5.32 in the book. All right, sampling. Basically, what this does is, the other day you did 10 samples, and each one of those samples was based out of the numbers 00 to 99. And then you took those numbers based off of the Gallup poll that said that 57% of Americans bought a lottery ticket within the last 12 months. Well, you kind of tested that. You had 100 numbers, so you had a sample of 100 numbers, all right? And that's what you did. You took 10 samples, and then you averaged those 10 samples. And remember, we got something very close to this right here, all right? Now, what happens is when we increase the sample size, I'm sorry, I'll talk about that in a second, but what happens is when you do multiple samples, I did a sample here and got 0.56. I did another sample and got 0.46. I did another sample and did 0.61. This dot, dot, dot means that we continued. We did more samples. All right. Notice the more samples we do, if we were to graph it each time, what happens is the graph becomes almost normal. And if you notice, if you look for the mean, the average, the mu, it's around 0.6. And remember, if you remember me telling you the other day, whenever the Gallup poll did all these surveys, they found that 57% of Americans in their samples uh, bought a lottery ticket within the past 12 months. Well, because they did it randomly and it was a large enough sample, they used that fact about the sample in order to generalize or estimate the parameter for the population. And that parameter turned out to be about 0.6. Now, I want you to notice something. The more samples we take, the more samples we take, the closer to the true parameter we will get. Now remember, you don't know what the true parameter is, but the more samples we take, the closer to it we will get. Now, when we increase our sample size from 100 to 1,523, like the Gallup poll did, we get closer to the true proportion. So that's what this next graph looks like. Notice they did a sample size of 1,523. They did it once, twice, three times, 4, 5, 6, and then they continued. Each time they did it, they got 0.609, 0.625, 0.579, which is really, it's even more close to 60. So what happens is when you increase your sample size, when you increase the sample size, you decrease variability. Okay, notice this isn't as spread out as this one was. Notice it's more spread out. Okay, now p hat has no bias as an estimator of p-value. Okay, this is your parameter. That's your parameter. It has p hat has no bias. This is true for both large and small samples, basically because you're taking a random sample. Now, in order to eliminate bias, you make the survey random, or you make the whatever you're doing random. Larger random samples have less variability. Larger have less variability than smaller samples. Bias is consistent. Repeated deviation of the sample statistic from the population parameter, that's your p-value, this is your p-hat, in the same direction when we take many samples. In other words, you're not going to get the same value each time, more than likely. You're going to get various amounts of p-hat. Now, variability describes how spread out the values of the sample statistic are when we take many samples. Large variability means that the result of the sampling is not repeatable. This is what you really need to know. A good sampling method has both small bias and small variability. All right, and we're going to look at this. Now notice, I want you to notice these dots right here. Here is my parameter. Notice that they're all really close together. That means that is low variability. But they're a long distance away from the parameter, therefore they have high bias. Okay? So the distance here means high bias. The tight knit means low variability. All right, let's look at this one. Notice that everything is around the center. That indicates, because it's even on this side and even on this side, all the way around it's even, that indicates low bias. Okay? But because it's so spread out, that means it's high variability. All right? High variability. So again, it's spread out evenly around the parameter that's low bias. But because it's spread out, it's high variability. This one is away from the center and it's spread out. Therefore, that's the worst one of all, high bias and high variability. This next one is the most ideal. It's not very spread out, so there's low variability, and it's right on target, so it's low bias. Okay, that's the most ideal situation. Now, this is the same scenario. This is the same scenario on this graph. This graph you'll see most of the time in the book. This is what you'll see on the test or a quiz. Now, notice it's spread out, so that's high variability. And because here's the parameter, notice it's not even on both sides. So that's also high bias. This one is the most ideal because it is close to the parameter and it's not very spread out. So that's low bias and low variability. On C, notice it's spread out. So it's high variability. High variability. However, it's spread out evenly around the parameter. Therefore, it's low bias. Now finally, this is not spread out, so that's low variability. But because it's so far away from the parameter, it's high bias. All right, next thing we're talking about is margin of error. I call it MO. Margin of error basically tells you if most of your data is at 95%, you're plus or minus 3%. In other words, your information, the true parameter, could be between 92% and 98%. It'll be somewhere in between there. Okay? Now, in order to calculate your margin of error, you do 1 divided by the square root of n, and the n is your sample size. Now, the Gallup poll had a sample size of 1,523. So 1 over the square root of 1,523 is approximately 2.6. But the Gallup poll reported it as 3%. Well, the reason why they reported it as 3% is A, it's cheaper to put 3% in print because you have 1, 2, 3, 4 symbols as opposed to just 2 symbols whenever you're printing. And plus 3% is easier to say than 2.6%. It's just a nicer number. Now, because the formula uses the square root of the sample size, however, to cut the margin of error in half, we must use a sample 4 times as large. So for instance, if my sample size is 36, so 1 over the square root of 36 is 1 over 6. If I want to cut my, this is my margin of error. All right, normally I would put it as a decimal. But let's say I want to cut it in half, so times 1/2. That would be 1/12. I have to increase my sample size by 4. So 4 times 36 is 144. The square root of 144 is 1/12. Therefore, if I want this to be 1/12, I have to increase my sample size 4 times. Okay? We are now the confidence interval. We are 95% confident that between 54% and 60% of all adults bought a lottery ticket in the last 12 months. Well, notice Gallup polls came out with 57%. If they're 95% confident with a 3% margin of error, that means 54% to 60%. They are certain that the true parameter falls between those two percentages. A confidence statement has two parts. It contains a margin of error and a level of confidence. You need to read these bullet statements, these 5 bullet statements. Let's see how much time I have. 11 minutes, okay. I'm almost done. Now, the variability of a statistics from a random sample does not depend on the size of the population as long as the population is 10 times larger than the sample. Variability of a statistic of p hat from a random sample does not depend on the size of the population as long as it's 10 times larger than the sample. Okay? Now, here are the questions that you're going to have to do for homework tonight. Here they are. I'm going to quickly go through them. There's 5.34, 5.35, 5.36. You can pause it if you need to look at them. 5.38, 5.39 and 5.40, 5.41 and 42, 5.44, 5.47, 550, 551, and 552. And that is it. Those are due tomorrow as a grade.